Monolith or modules, using microservice concepts in React. A few words about me. My name is Kristian Mandrup. I taught myself how to code BASIC back in 1985 when I was just 11 years old. I've been an IT professional for over 20 years, since before the internet took off. Find me under Kristian Mandrup in one word on GitHub. I mostly experiment and create my own tools, libraries, and frameworks. I also contribute to open source that I find interesting and valuable. I've been through so many languages, frameworks, and technologies that I don't really care about the specific technologies anymore. When you've been in this long, you come to understand that it is all about using architectural concepts and engineering practices, not about the specific technology. Technologies come and go, the best concepts and practices stay the same. Architecture and teams, divide and conquer. In a typical modern architecture, we still use a monolithic frontend. A modern backend, however, is typically designed as a set of decoupled microservices. This presentation will look into how we can reuse concepts of microservices for the front end, also known as a micro frontend. Note that a modern full-stack app is often divided into three distinct layers: the front end, the API connecting front end and back end, and of course the back end. Ideally, we would like a fully decoupled architecture, i.e. no direct dependencies, where any of these layers can be changed without impacting the other layers. In the full stack, each engineer will have to work on and master the full system, front to back. Each team and engineer might work across the vertical layers or horizontal business domains, or both. We would prefer for each team to own a specific business domain, a bounded context, front to back, each forming a separate application. When adding a new feature, we would need a lot of communication between teams when using a layered team split. When using micro frontends, however, each team fully owns a new feature, meaning little to no inter-team communication is required. The specialist teams each consist of specialists for a specific layer in the architecture, whereas each cross-functional team consists of a set of different specialists spanning the entire workflow to implement a given feature. Each cross-functional team has a specific mission in terms of delivering business goals with business metrics, as opposed to engineering goals, which is typical of the specialist teams. In a micro frontend, each team is responsible for a set of separate pages or fragments that make up a separate micro app that is fully decoupled from the rest of the application. The applications are assembled and composed in a shell or container application. This means that the development process scales much better as the project grows, with the same benefits seen for microservice architectures. The React monolith, trouble in paradise. In a monolith front-end app, typical for most React web or mobile applications, the app is most often partitioned per layer, as was the standard in MVC frameworks such as Ruby and Rails. We often see one folder for the App Store or model. The controllers are the selectors, reducers, and API integration, such as thongs or sagas. The specific controller methods might be grouped by business domain or by specific controller method type, i.e. one folder for all the API functionality and so on. The view is a React component, rendering a view model state and using dispatch to communicate events back to the controller. The view often contains its own business logic as well, i.e. an MVC model in itself. Some of the main problems with the monolith approach. Most of the code is not collocated. Tests are often not collocated. It has a high complexity. It has mental overhead, keeping track of code dispersed across the code base. It results in merge conflicts, lack of good structure, all or nothing releases, difficult to onboard new team members, and development does not scale well as complexity grows. Modules. Ideally, we would prefer modular design where each module contains all the logic to implement a specific bounded context. It would be much better with a modular approach, i.e. micro frontends. Ideally, each such micro frontend would live in a separate repository, just like a microservice. The benefits of this modular approach are as follows. Code is collocated. Tests are collocated. It has a minimal complexity and minimal mental overhead. Merge conflicts are quite rare. The module is the implicit structure. so it has strong cohesion built in. Small independent releases are possible. Easy to onboard new team members, as it is quick to understand, simple and an independent module. It scales well. Complexity is linear per module. One ring to rule them all. Redux or Flux. The Flux architecture, such as Redux, is essentially no different than classic MVC, a unidirectional data flow. The view subscribes to a specific subset of the model through a selector. On user interactions with the view, actions are dispatched to the controller, which may communicate with one or more external systems, i.e. side effects, before reducing the model to a new state, which is then reflected back in one or more views. The views can be seen as materialized views, a database concept. Good engineering principles dictate that the views should be stupid, i.e. little to no business logic. Controllers should also be stupid, mostly just message conversion back and forth. Models ideally should also be stupid, just like tables in a database, which leaves dedicated business services to implement the core business logic. Clearly, the typical React component architecture with Redux does not really adhere to engineering best practices of MVC. Components are most often mixing view, controller, and model logic so that complexity gets out of hand. Redux does not really have a separate service entity for placing application business logic, also meaning dispersal of the logic. This all means that logic is fragmented across the stack, making it difficult to maintain and upgrade. This also makes it very difficult to port the MVC partitions to new technologies. The main issues with Redux is a meaningful framework, which means little to no heavy lifting is done by the framework itself. It has a lack of strong conventions beyond a structural guideline. It leads to a lot of manual hand wiring, no specific place for business logic. It's all dispersed across the stack. It's difficult to reason about and debug. On a personal note, when I first started using React, I was initially very excited. But I was quickly frustrated with the amount of boilerplate required when using Redux, which led me to write a generator to help generate all the boilerplate for me. However, code is a liability, and having to use a generator is really a code smell. I ended up discarding React initially for a long time due to a lack of a sufficiently good state management solution. One ring to rule them all. Take two. Microservices. In a microservice architecture, we have an API that takes one or more incoming events that are then dispatched onto the event stream. All events on the stream are logged in an event log, which makes it possible to replay any part of the complete application event history. Services can subscribe to the stream, selecting specific events of interest for the service. The service maintains its own store, also a materialized view. The service can publish new events on the stream, such as the result of processing an event. A view store can subscribe to specific data events, generating a materialized view. A broadcaster service can listen to the event stream or log and broadcast specific events to other clients to keep them in sync. An API request may also use a broadcaster linked to a view store to provide a specific view of the app, such as a particular domain or domain model. Some of the advantages of the microservices architecture. We use publish subscribe instead of point-to-point communication, which means much better decoupling. We have the complete event history stored, which allows us to playback, tracing, and much more. We can enable independent releases very easily. Technology can be changed incrementally or case by case by substituting or modifying services. It's easy to onboard new team members. All functionality is in its place and not dispersed across the stack, and it's easier to scale in terms of performance, and there are many more benefits. The view acts as the input API, dispatching events to the event stream. The view also acts as the output API, selecting events from a materialized view, i.e. the view store. An API service subscribes to the event stream or view store to dispatch API calls to external systems. Another API service subscribes or calls an external API to retrieve data published as events on the event stream. The event stream thus acts as the unified gateway between all actors in the system. To put this into practice, we can use the browser message bus API, possibly with Polyfill for inter-app communication, i.e. for communication between the different micro frontends. We can use Seneca.js as a unified transport layer. It supports many different transports on both the front and back end. And we can use RxJS as the event stream infrastructure. We can group the microservice parts into the following. React component, i.e. the Vue IO. Service, Vue Store, which is a materialized view of the App Store, and an API integration service. We can furthermore partition the React component into its own MVC pattern to follow good engineering practices. Note that the MVC partitioning is most relevant for components that both take and display input, such as forms. A React MVC component might look as follows. The Vue publishes a Vue event. The controller subscribes to the Vue event and translates it to a business event. The business event is then used to reduce the local state via the model. The model validates the event and the state is reduced. The view is updated optimistically either with the error or the new reduced state. The controller dispatches a successful business event to the event stream for further processing by services. The architecture sketched out might look a bit complex at first sight. However, due to the strict adherence to good engineering practices and conventions, we can drastically simplify the code footprint while capturing all the benefits of a very clean architecture. Don't write code. Write code that writes code. Encapsulate patterns. Boilerplate simply does not scale. Let's look at some sample code now. Notice here that the view has a model and a controller. The view is completely stupid, having no logic other than dispatching of events. Good engineering practices for views. Sample product controller code. Here we simply subscribe to a product event and forward the data to a form controller. The product validator class is responsible for validating the product and belongs to the model. The base view model, and base view controller encapsulate the core patterns. In reality, much more of the code could be parked here, so that entity-specific code in most cases almost entirely disappear, relying on built-in conventions. Also note that we should avoid inheritance favoring composition in real life. Using composition, we can substitute functionality as needed, replacing our conventions and core infrastructure logic in one fell swoop with a simple change of configuration. This also makes adding logging and metrics much easier. Here's an example of a base form controller. Again, we should really use composition. Notice how elegant and easy to follow the code is. This code would apply to any form across the entire app. The business service contains business logic and should consist of a model and a controller class. The API service should consist of a model, API, and a controller class. The controller subscribes and publishes events to the event stream. The API communicates with the API gateway. The view store is a materialized view and should consist of a model and a controller class. The controller should subscribe to the event stream. The full micro app would look as follows. Components, i.e. views, business services, view stores or materialized views of the application store, and API services. This pretty much mirrors the backend architecture, so we have a unified architecture from front to back. The full application would consist of the micro frontend, which is a micro app, and a micro backend, which is also a micro app in itself. The The full micro app would implement the front to back functionality for a specific bounded context. The micro app can be versioned and released as a whole, being fully independent and isolated with no direct dependencies. The micro frontend and micro backend can also be released independently. We can ensure the backend doesn't break on incoming API messages by validating and discarding messages that don't conform to expectations. The same can be done to the front end. This ensures that if we release different versions of either front end or back end, the system will still work as expected and won't break. So long, and thanks for all the fish.